Test. Test. Yeah. Test. Test.
Yeah.
Thank
In
you.
your pocket.
Ah, yeah.
Um, okay. Welcome back, people. So this is our third session, and I know that people are reluctant to stop their lunch and come back, but I think it's time to start. Um, First talk will be given by Florian. This is a work done in collaboration with Matthias, Carlos, Armin, and Supratik, and it's going to be called transmuting clauses.
Right, thank you. So I will start talking about transmutation, which is a cool name and in-processing technique for SAT solvers. So that's why I start talking about in-processing. And in-processing is great. I love it. Why should you care? It's first of all, it's important for the performance of state-of-the-art SAT solvers. So modern SAT solvers really don't just do pre-processing on the formula. Every once in a while, they will revisit their pre-processing algorithms and just use them on the current formula. And this really seems to help in the grand scheme. And other than that, well, pre-processing is largely independent of the CDCL algorithms, so you can really can use it as a big playground. You can just take anything you want to do and try it out in pre-processing or in processing in a SAT solver. And you have no risk of breaking the whole solver. Of course, if you do dumb things, you probably won't improve the solver. At least you're only spending some time and you're not hurting the performance as much. So, right, that's why for our idea transmutation, we chose pre-processing um, as just to try it out. But before I get to transmutation, I want to explain hyperbinary resolution because it's related. So it's the main idea of hyperbinary resolution. You take a big clause, large clause maybe, and then you take a bunch of binary clauses of size 2, and you derive just a new binary clause. Why would you do that? Well, binary clauses are great. If the whole problem were just binary clauses, every SAT problem trivial. But other than that, like they kind of fix an issue with propagation. If you just decide on a single value and propagate the result, then a bunch of implications like A implies B. If you now, like logically, you know that not B should imply not A. If you just do propagation, this doesn't hold, not necessarily. So if you decide not B and propagate, you might not get the result that you expect. And what binary resolution, hyperbinary resolution does, it kind of fixes this, at least on decision level 1. So when you just decide on a single value. So if we do hyperbinary resolution, we get this free. And we learn lots of binary clauses. That's great. Maybe not so great because there can be quadratically many of these and they may not help. So, right. Now let's go to transmutation. I said it was related. It's kind of an extension of hyperbinary resolution. So we also take a long clause and then take a bunch of binary clauses and we combine them and resolve them to get a new binary clause. And I will explain this in detail with a slideshow. We have the long clause. And each literal in the long clause, it implies a set of other literal propagation. So here in my example, we have L1 to Ln, and each one of them, for simplicity reasons, implies a literal with a nice letter instead of just index. And we concretize the example. So we just get a clause of size 4. And let's assume these are propagated literals for each one of the literals in the clause. So really what the algorithm does, it decides literal L1, it propagates the result and it remembers like all of these literals that it propagates. And then it backtracks and proceeds with L2. And then in the end, well, what we can do from all of this information, we can pick a set of literals that were propagated that kind of cover the original clause. So here, if we pick B and G and E, we cover every path, every literal in the clause. And we know that if the solver at some point decides not B, not G, and not E, from the fact that like these implications should go both ways, the clause here that we started with will give a conflict. And we want to avoid this conflict. So we want to help the solver not decide like B, not B, not G, and not E at the same time. So we could learn this clause, but I told you before we want to only learn binary clauses because they're nice. So that's why there should be a next slide. There is a next slide. Nice. Right, we have to always restrict ourselves to only picking two literals. And in our example, there are two literals that we can pick. So we pick A and F, and we get a binary clause. And we can learn this clause. It follows from resolving the implications. L1 implies A, L2 implies F, and so on. And then the big clause. So now we can ask ourselves, well, should we learn this clause? And at this point, we don't know, right? It might be helpful in guiding the search. It might just not be helpful. Probably shouldn't learn it then. Anyhow, we have a way of distinguishing clauses that we want to learn. And in this case, this is one that we don't want to learn. Because if we look at this example, when the solver decides not F, then the big clause up there actually propagates. And it propagates the literal L1, which in turn will propagate all the literals to the left. And in fact, it will also propagate A. So in this case, if we decide not F in the beginning and just do unit propagation, we will already avoid the conflict that we wanted to avoid by learning this clause. So there's no point. And in fact, that's how we distinguish good from bad clauses. We just try to like probe again. So decide either not A or not F, and then propagate. And if the other value propagates, we skip learning this clause. So luckily, there are also literals that we can pick, do not have this behavior, at least on this example in the local scope that we can see. Right, so this is an example of a clause that we would want to. And I have an overview again. So transmutation is trying to extend hyperbinary resolution to avoid conflicts, instead of just getting implications. And it learns binary clauses, and it uses lots and lots of unit propagation. So as I said, in every step, we basically do one decision and then perform unit propagation. And we also do this when we want to know if the final binary clause that we derived is actually good. So there's a bunch of unit propagation. There can be lots and lots of these candidates. So when I go back one slide here, like every pair of these literals could be a candidate of a binary clause that we want to learn. So we want to check each of them. But of course, there's quadratically many pairs in the number of propagated literals. So there are quite many. And along the way, we perform unit propagation on these potentially quadratically many pairs, which is also really expensive. So right now, this is maybe not usable. So let's look at some partial solutions. First of all, right, we could see from the Bayes algorithm without any optimizations that this is probably going to be an expensive technique. So what we want to do is we want to schedule it smartly, not just throw this, not just run it until it's completed and then get back to CDCL, because by that time probably our timeout is gone. So we insert checks to like limit the runtime of the procedure. And then we can also insert early aborts that will know when maybe the initial clause we picked cannot, like we cannot derive anything from it. You can also early abort, and that's the first thing, like limit the technique, don't let it run forever. Then next, optimization. So when we pick the initial clause, of course, we would expect like short clauses to derive more binaries, because we need to cover the clause. And what are the chances that every literal in the clause will propagate the same literal down the line? So short clauses, the chance is much higher. So we want to fix the maximal clause length by that reason alone, because probably there's no point to look at longer clauses. But also a neat thing we can do is when we just want to derive which binary clauses would cover the entire big clause, is we can just, we fix the clause length to say 64. We can just do a bunch of bit string operations, just a bit mask basically, to tell us whether our current candidate pair will cover the clause. And this speeds up like the selection of the binaries. Right, the next thing, of course, we restrict the binary clauses that we learn heavily, right? Because we want to get clauses that actually prevent conflicts and cannot just be derived by hyperbinary resolution. Like one reason for this is because we're doing this in Cadical, as one does, and Cadical already runs hyperbinary resolution, not to completion, but it runs it. So we probably don't want to derive clauses that could be derived otherwise. And actually one way of speeding up or limiting the number of candidates for these pairs is, well, if we have a literal that is only propagated once, we can't use it because the only way to cover the rest of the clause is to have a literal which is propagated by all the other ones. But by our logic, this literal would, in turn, if we negated it and probed it, would propagate the long clause we had in the beginning. So there's just no point. It would be bound by hyperbinary resolution, so to say, or yeah, right. So this is how we can do the pre-selection of the candidates to limit this quadratic algorithm that we have to do. Right, and then another thing on the slide here, which is not an optimization of the algorithms, but just an extra thing that we can do, actually, when we do all of this probing, right? Of course, if we get a conflict, we can just learn a unit and such things. So there are small optimizations there, but when we probe a literal in the clause and propagate another literal in the clause, we know the literal that we probe to begin with is actually redundant, so we can erase it from the clause. We can shorten the clause that we looked at. And that actually happens. So we can, even if the entire technique does not derive any binary clauses at all, we still get some benefit from shortening maybe some clauses. Right, and I should also mention the smallest size of clauses that we're looking at is 4, because otherwise, again, hyperbinary resolution would find any clause we want to derive for sure. Right, so here's the first slides with experiment. As I said, we did this with Cadical, and these are at competition 2022 benchmarks. And as you can see, it's kind of close, right? Transmutation seems to be a little bit worse. And right, so what we can take from this is maybe definitely our limiting of the technique works. So we're not hurting the solver, right? We make sure that transmutation is run only a short amount of times every in processing, and this may cost a little bit, but it's not hurting the solver much. But we can also see that really we're not gaining a lot, or maybe nothing at all. And maybe we should look why that is. So, I have a plot with, actually, maybe that's not reasons why, but that's interesting data. So these are the clauses, actually the original clauses that we picked that were able to learn binary clauses, from. And this plot starts at 4 and ends at 42 for unexplained reasons. No, actually, it should extend to 64 really, but it wouldn't fit on a slide. So, right, and we can see that there are many clauses with length 4 that we can learn binaries from. And the range goes, like there's a spike at length 10. And then there is really not a lot here in between. Maybe surprisingly, there are some really long clauses where we actually learn binaries. And I suspect this is a benchmark thing. So have to look at the benchmarks where this happens. But really, yeah, it's apart from this is expected. Like there's some clauses where we like mostly short clauses where we can learn binaries from, and the total number here is actually not that high. So these are all the clauses from the entire 400 instances from the benchmark set where we could actually learn applying this technique. But that may also be because we're heavily limiting how long we run the technique, right? Otherwise, the runtime would blow up. Here are some more statistics. So the line is the overall propagations of the solver. And then we have the propagations performed by transmutation. So that's the second line. And these lines are all sorted independently, but you kind of see the general trend that we're really limiting the factor of propagations performed in transmutation by just some constant factor of the global propagations. So you can see this really nicely in the plot. And you can also see we're scheduling a lot, or I don't know if it's a lot, but we're scheduling clauses for transmutation, the dark blue line. But the clauses that were successful is like way smaller number. It's actually the lowest. So there's a large gap between scheduled clauses and clauses that were successful. But we also have this red line, which is the number of clauses that were checked. Right, and there's already a big difference between clauses that we schedule and clauses that we get to check, because we have to abort the technique once it gets too expensive. Then you can also see the quadratic, I don't know if like the candidate that we get is the number is quite high. So propagate lots of literals that we have again. And here, like some clauses can be shortened. Maybe the most interesting of binary clauses that we learn, so I call them golden here, because we're putting long clauses to get golden binaries. Yeah. So we don't learn a lot of binary clauses, and there are also quite a few benchmarks where we cannot learn anything. Right. So what I want to take away from the previous plots, and also from this whole thing is like there are still ways to improve it, and maybe a simple one would be finding a nice heuristic for the clauses we pick, because we already know we cannot check every clause, and we're scheduling a lot of them but not checking a lot of them. So maybe there's a nice heuristic that we can apply that will allow us to get more successful attempts. Another thing is, because we're doing all of this propagation anyways, why not try to share the propagations we do between clauses? So right now, every time we get a new clause, we delete all previous knowledge, propagate again, and maybe like especially when we don't learn anything, we can just keep all the information we already have. Of course, we would need to select clauses with many similar literals. Otherwise, sharing, there wouldn't be any point in sharing, but maybe one could check a lot more clauses this way. Another thing which is inspired by other in-processing techniques, such as vivification, is asymmetric probing, and also the shortening of the clauses is inspired by vivification and or instantiation, for those of you who know these techniques. So the idea of asymmetric probing is, in this case, the first literal. So we fix an order of the literals in the clause to begin with. And then we propagate the first literal positively, because we propagate all of them positively. And then the second one, before we propagate the second one, we actually decide the first one negatively, propagate, then the second one positive and propagate. And we continue this. So for any literal, we decide all the previous ones negatively and then this literal positively, and propagate the result. And this way, when we do the final check for the binary clause, which covers, like when we do the covering check, we're still guaranteed that we're able to learn the clause. So we're still allowed to resolve all these clauses against each other and learn our binary clause. And this just might allow us to like get more that are maybe interesting. And then finally, of course, because this is implemented in Cadical, we want to have LRAD proofs. Right.
Thank you very much. Thank you very much, Florian. We have a couple of minutes for questions. Questions? Do we have a mic?
Thanks for the nice talk. So what I'm taking away is that it might be very helpful to get all of these transmuted clauses, like golden clauses, but you're doing it really, really cautiously. So not to spend any unused, not to spend too much cycles on it, basically. So if I could just do this for free until completion, right? This transmutation. So for example, if I'm in parallel solving and I have just one thread the transmutator who does this all of the time, what do you think is the ceiling? How much this might help solving? So is this really promising? Did you do experiments where you did this less cautiously?
Well, so I didn't do the experiments. Carlos did some experiments in that direction. So what he did is learn these clauses outside of the solver and then give it back to the solver. But I'm actually not entirely sure of the results. So I believe there's some promise to these binary clauses. I think it's kind of limited, and it might, even if with further optimizations, it might not be worth it. Maybe if you're Amazon, you can run a small computer on it and it doesn't hurt you. But yeah, I don't know if it's like you want to dedicate an entire thread to it. Maybe there are more promising processing techniques that could do more.
Okay, thanks.
Any other questions? Well, I have a couple related to experimental results. So you showed us that, yes, this slide. My understanding is that you took Carico heuristics and processing techniques. I think it makes sense to kind of try to disable many other processing techniques because they may affect the silent. The original. And then what is the
Also, really hard actual actually happens is change the watch. So this effect alone impacts unfortunately make anything. But
next question? One of the motivations for the conflicts here. Then you try to compare the number of
so the reduction up down might even just overspend. Maybe it's
let's thank the speaker. Our next talk will be by just trying to find her line. The next speaker will be Dominic Schreiber, going to give a talk on the work called An Empirical Study on Learning Overlaps. So work is done with Annick Borowitz and Sanders.
Right, then hello and welcome. I'm talking about an empirical study on learned clause overlaps in distributed SAT solving. So this was a one-year research project done by Yannick Borowitz and supervised by Peter Sanders and myself. So let me begin with a little analogy to introduce like parallel and distributed SAT solving. Consider we have a large logical puzzle which we would like to solve, and we have a number of n logic experts which to solve this puzzle in a cooperative fashion. Now, the thing is that our experts are rather antisocial or unsocial beings, so they tend to work the best if we just leave them undisturbed while they are doing the puzzling. So how do we coordinate our experts the best? Well, the approach I'm talking about today is that what I call a cooperative portfolio. So essentially, all of our experts just work on the original problem independently. And since everybody has their own strengths and weaknesses and approaches, everybody will arrive at different partial solutions here. And now we periodically conduct some brief stand-up meeting where each of the expert has the opportunity to share the most crucial insights they gained, right? So one of the experts may share that at the position 1, 2, there should be the number 6 in the puzzle. And now all of the experts can integrate those insights into their own solving progress in order to accelerate their solving. And in the end, we are done as soon as only one of our experts is able to find a complete solution to the problem, right? In this little analogy, I'm of course talking about parallel SAT solving. Our different experts correspond to different sequential SAT solver threads, so mostly CDCL solvers. And we diversify those sequential solver threads differently via, for example, setting different configuration options or just different random seeds. And the shared information among our experts are which our solver threads are learning during their exploration of search space. So the state of the art in distributed SAT solving specifically, where we have many machines at once, is MALOPSAT. And I will talk about that system in detail 2 talks later. So for now, just the general gist is that that system performs periodic all-to-all clause sharing, so everybody can share their clauses with everyone. And this is a scalable operation between all of our solver threads, where we can immediately detect clauses that are actually duplicates during the aggregation. And we also filter clauses which have already been shared recently. So we won't reshare them immediately again. So this works surprisingly well. And we got some speedups compared to the state of the art. However, in most cases, the system still scales strongly sublinearly. So if we invest 10 times the number of resources, we won't get an acceleration by the factor 10, but actually much less, right? So we wondered how we could improve on that, or how we could even get to know how to improve on that. And one question we asked ourselves is, how diverse or in other terms, how redundant is the work which our solver threads are performing? So we looked for a metric which might capture something like that. And now what we try to answer is we wanted to explore the overlaps in the learned clause sets across our solver threads. So how diverse are the clauses which our solver threads produce? How big is that overlap? Can these overlaps maybe serve as a sort of proxy for the redundant work which the solvers perform, which we want to? Can we also gain insights on suboptimal solver design based on those learned clause overlaps? All right, so first of all, we need to gather some data to explore this. And what we want to do, we run our solver, our distributed solver on some large, log all of the clauses produced by all of our solver threads together with some different kinds of metadata. Now, since we're in distributed SAT solving, we get many millions of clauses that are produced each second. And then also analyze all of them may not be so feasible. An approximate approach, we apply a 64-bit hash function to a produced clause, and then we only log and report hash value is divisible by 16. So this gives us a sampling factor of 16, and so we have less clauses to vary. So we essentially cut off 4 bits of our hash value. And then what we actually report with a clause is its timestamp of logging relative to the beginning of solving, then which particular solver thread produced the clause. So that's first the index of the process that produced the clause, and then the index of the solver thread within the process that produced the clause. We also log the length of the clause and the literal block distance score of the clause. And now note that the literals of the clause themselves are not in there. So we don't log the actual clause, but we approximate it with our hash value. And that means that we might get collisions where we say that, oh, this clause, this is a duplicate, but actually it was just a hash collision, right? So we looked at how likely that is, and we found that even if we hash 1 billion clauses, we get less than 1 expected such hash collision. So we can just neglect those and just consider our clauses based on this hash function instead. That makes evaluations and all of the analyses efficient. Now we have a set of reports. R, note the set of unique hashes in that report as H of R. Now we have 2 metrics in order to see how our clause overlaps look like. First of all, in order to measure the overall overlap of our produced clauses, we have the duplicate clause production ratio, like the DCPR. And this is simply the ratio of clause hashes that are non-unique. So we take all of our unique hashes, or we take all of our reports, and then we subtract the number of hashes in there and compute the ratio over all of our reports. The second metric is meant to measure the overlap between a particular pair of solver threads. That's the pairwise produced clause overlap, or PPCO. And this is just the Jacquard index, which is used to compare the similarity, or to measure the similarity between 2 sets. So we compute the intersection and the union of the set of unique hashes, which we got from our 2 solver threads, and then we divide them, the cardinalities. So that's the Jacquard index. Okay, so tricks we use. Let me briefly explain our setup. We use malloc SAT, the distributed solver, and we cycle through 3 different solver backends. We use KSAT, Cadical, and LinkLink. We allow the sharing and the logging of clauses up to a length of 60, which captures most of the clauses that are produced by those solver threads. And we employ different kinds of diversification, like random seeds for each solver thread, or setting some variable polarities differently for each solver thread, and configuration options which are specific to a certain solver backend. We use 2 HPC clusters. I think I don't need to go into detail. One of them has 2 sockets with 24 cores each for each compute node, and the other one has 38 cores for each socket. But yeah, so we're basing our analysis mostly on the instances of the SAT competition 2022. In some experiments, we limited this to a set of instances which some solver in the competition was able to solve. So this takes away the most difficult instances, which we're very unlikely to solve either way. So this saves some resources. And we impose a wall clock limit of 300 seconds for each instance. So let's take a look at the results. What is the main takeaway for this study? So first of all, an overview. How large is our duplicate clause production ratio between 0 and 1 on one node, on 4 nodes, and on 16 nodes? What we can see is at one node, only around 5% of all clauses are duplicates. And at 16 nodes here, about 35% of all clauses are duplicates here. However, this is actually a bit less than what we would have imagined. Like at 16 nodes, that's 768 cores of running our distributed solver. Still, about 2/3 of our produced clauses are still unique, right? And that's kind of more than we thought. We also looked at how our clause length plays into that. So how is the distribution over the clause length, both over the produced clauses, that's the blue bars here, and then over the ratio of the duplicates that we got. So what we can see here, first of all, is that the clause 10 and below tend to have the highest overlaps. And this is not really surprising. You can make a statistical argument that solvers are more likely to produce the same short clause than the same large clause. And what we also see are two extremely pronounced peaks for unit clauses and for ternary clauses. So here we can see that, first of all, really many clauses are produced of that length. And secondly, there's really many duplicates in there. So we later tracked this down to specific pre- and in-processing techniques, at least partially, which I'm going to talk about a bit later. So we also looked at the DCPR for different benchmark families. And here I just have some of the extremes. Right here at the left, we have the family we looked at using Marco's benchmarking tool, GBD, which he's going to talk about later this week. The family and the result, and then here the DCPR distributions. And like on the one extreme, we see the families with an extremely low DCPR. So those are instances where all of our solvers basically produced only distinct clauses, and there are hardly any duplicates, right? That's, for example, the pigeonhole formulas, and also equivalence checking, graph isomorphism. And what I think is that those are instances where you can derive really, really many distinct clauses, and you also need very many of them in order to arrive at a proof, right, for the unsatisfiability. So these are instances where all of our solvers can just derive many clauses. All of those are different. And in the end, this also parallelizes nicely, because those are, as a matter of fact, also some of the benchmarks where our distributed solver has the best speedups. And conversely, here are some benchmark families where the overlaps in the learned clause sets are extremely large. For example, here, some planning benchmarks or benchmarks from software verification, which are model checking instances. Those are very large formulas with a particular structure. And as it seems, all of our solvers are almost doing the same work in terms of produced clauses. So there seems to be like one way to simplify and process the formula. And also, consequently, those are benchmarks where our solver does not scale very well. So there seems to be some correlation, at least. We also looked at how those clause overlaps are distributed along the temporal axis. So first of all, we noticed that the vast majority of duplicates are actually produced in the first few seconds of solving. Yeah, for example, we noticed that we got a median DCPR of 28% after only 3 seconds of running, right? So 28% of duplicates, and that already makes up around 80% of our full runs duplicates. So my intuition is that the solver threads are initially very closely together, and then they fan out in a way, right? And now we also wondered what's the duration between a clause's first production and the production of its duplicates, right? So how closely temporally correlated those are. And here you can see the distribution over this duration. And here you can see, for example, that about 60% of all duplicates are produced within 4 seconds after the clause has been produced for the first time. All right, so they are pretty closely correlated with each other, and they co-occur at a similar point during solving. We also, now you might think that this is only because most of our runs are very short, and that is true, like many of our runs only take a few seconds. However, we also looked at this for instances which take at least a minute to solve, and the results are still similar. So still about 50% of the duplicates are produced within 4 seconds after the clause's first production. Okay, this does explain an effect which we noticed in recent work. MATLAB features a filtering approach where recently shared clauses are prevented from being reshared again. And we found that this filtering works especially well for short horizons, like if you only remember a clause to have been shared before for a few sharings or for a few seconds, right? Whereas you quickly get diminishing returns if you're increasing this horizon. And this essentially explains why we just have those temporally correlated duplicates most of the time. Now, brief look at the impact of diversification of our solvers. The main thing I want to take away here is that with our baseline, we have around 35% of duplicates, whereas if we disable our variable polarities, which we set differently for each solver thread, we get a substantially higher DCPR, growing from like 34 to almost 50%. So this confirms that setting those variable polarities really has a large impact on which clauses the solver threads produce. We also tried to just disable clause sharing and see what happens there. And what happens is that we also get an increased DCPR from 34 to 41%. So this confirms in a way that our clause sharing itself also participates in diversifying the clauses that are produced afterwards, right? Which is a nice. Our clause sharing, the solver performs substantially worse, but I'm talking about that in my next talk. And now we looked at the pairwise overlaps between particular pairs of solver threads. So what you see here at the left is a matrix of each pair of solver threads within the first 2 processes which we start. So the processes are divided here by the white lines, and the gray dashed lines are like individual repetitions of the solver backends. So it's always Cadical, Kissat, Lingeling, Cadical, Kissat, Lingeling. And what we see here for the mean pairwise produced clause overlap is that the lower right cell here is always the brightest. And that means that pairs of Lingeling solvers in that experiment have the highest overlaps with each another rather than taking any other pair of solver backends. We also looked at the maximum produced clause overlap. And here you can see that generally we have these diagonals. So the same like pairs of solver threads which share the same solver backend have higher overlaps than other pairs, which makes sense since they share the same implementation. We also look at those pairwise overlap if we only use Cadical, like just run Cadical everywhere to get a cleaner picture. And what you see here are somewhat pronounced diagonals. And that means that the pairs of the same configuration of the solver have larger overlaps. So here again, with these dashed lines, you can see when a number of solver configurations repeats, right? So if we use the same configuration, we get higher overlaps. That's also pretty clear. We did see some configurations where we have smaller overlaps in produced clauses overall. And that concerns, that's these black or these darker lines that you see here. And that concerns especially configurations where we modify our restart intervals and where we flip the default phase, right? So with those configurations, we get very diverse clauses compared to others. What you can also see, or at least I hope you can see, is that we get higher overlaps for pairs of solvers that are within the same process. So that's visible by considering that the upper left square and the lower right square are a bit brighter than the upper right and the lower left square. So that's the solver threads that belong to the same process. And there's two possible explanations for that. First one is that our first process always lives the longest if we launch all of them, due to the way how MATLAB launches our processes in a distributed setting. So we can just have a possible data bias that this process always reports the most clauses. Another explanation is that we share clauses along a tree-like structure of processes. And so our clauses arrive at different points in time. And solver threads within the same process receive the clauses like at closer points in time than if we take two solver threads that come from different processes. Then we also looked at the picture for the KISAT solver backend of MATLAB. And what we saw is that we get much higher overlaps than what we got for Cadical. So you need to look at the legend here that we get up to 11% of overlaps. Yeah, and overall a brighter picture then. So this, to a degree, may explain why in recent experiments our KISAT portfolio in MATLAB performed somewhat worse than the Cadical portfolio. Just the work being performed is more redundant. We did see low overlaps for specific configurations again, that again concerns altered restart intervals and also disabling specific or almost all simplification techniques, the in-processing. So that made us a bit that sounded or looked a little bit suspicious. And if you remember, we had this extremely pronounced peak for ternary clauses in our produced clauses and also in the overlaps. So what was our main suspect was KISAT's hyperternary resolution, which produces those ternary clauses. So we just tried to turn it off. And now if you take a look at this matrix, it got substantially darker. Overall, the overlaps in the learned clauses decreased substantially. We saw that the DCPR drops from 47 down to 33%, and we also got better performance. So this is a technique where we could pin down, due to the data we gathered, that this might not be, this might be a problem for solving. Then we also upgraded the solver backend in our solver to KISAT 2023, which dropped several in-processing options, such as hyperternary resolution. And with that new backend, we indeed got much lower overlaps again. So here you need to look at the legend again, and we only see overlaps up to 5% and something. This also leads to better performance, but this may also be due to other changes in KISAT 2023. Okay, so after all of these findings, we wondered whether our findings could also translate to improvements in our solver. So we tried 3 tiny changes, hoping that it might change something. First of all, we turn off the hyperternary resolution in our KISAT. We still use the 2020 version here for comparability. And then we somehow split how many unit clauses we export. We saw that this huge peak in produced unit clauses mainly comes down to Ling-a-Ling. And we thought that, well, we didn't really find a way to like a specific technique to disable. So we just said, okay, let's just wind down what Ling-a-Ling exports so that we don't clog our clause sharing with all of the redundant unit clauses, which are always preferred by our sharing, right? So this is a problem. So we say that the ith Ling-a-Ling in our portfolio only exports units where the hash value leads to a remainder of I or I+1. So we have a bit of the Ling-a-Ling threads produce unit clauses then substantially less redundantly, right? And lastly, we try to make use of the diversification which we're apparently getting by the different points in time when clauses arrive in our solvers. We just delay the ith solver thread's first successful clause import by some amount of import queries. All right, so what are the results? Well, we saw that our DCPR decreases drastically from 37 down to 22%. So that's a success. However, our performance improvements were really mild. So we only saw a geometric mean speedup of about 2.7%. and only around 58% of instances were solved faster at all. So, like, convincing. Apparently, this is not a great measure for redundancy and for performance. So why is that? Well, there's two main reasons I would argue play a role. So the first one is that some tasks in a solver that are just not reflected by an exported clause. So there is no witness for the work performed. And conversely, there's also some bursts of exported clauses, like from some in-processing techniques, which are very inexpensive per clause. So they are also a poor indicator of redundant work that's being done. All right, so let me conclude. Our central findings in the empirical study were that the produced clauses in distributed solving are maybe less redundant than one might expect, or what we expected. We saw that the duplicates are often tied to certain in- and pre-processing methods, and they often co-occur in close succession. In terms of diversification, we found that variable phases and restart intervals mostly have a large impact on the produced clauses. And we did find some explanations for earlier observations we made, such as the poor performance of a key-salt portfolio and the benefit of short horizon clause filtering. So our study has some limitations, which I don't want to neglect here. We only considered the syntactical equality of clauses, which is rather specific. You could also consider like stronger or more general notions like subsumption relations or others. And we also only considered a black box approach with unmodified solver backends, and tracking the actual provenance of individual clauses that were produced might really help to get deeper insights. Lastly, we only considered MALOP-SAT with 3 solver backends. So what about other systems? Well, we invite you, if you have a parallel solver lying around, to try our tool. Yannick has written a delightful little tool where you just plug it into your clause export interface, and then it produces all of the data and the plots for you. So if you want, try it out. And thanks for your attention.
Thank you very much. Do we have questions? Yes, we do. There is a hand there.
Hello. You mentioned subsumption at the very end, and it is in my understanding that SAT solvers usually don't perform subsumption because they're when they clean up the clause set, subsum clauses will naturally disappear. But in the context of distributed SAT solving, since you know that the good clauses you are sharing with all your instances, would it be now worth it to check separately for, once for every instance of SAT solvers at the same time?
So what you mean is check the shared clauses for subsumption, or?
Yes.
Yes, I think that might make sense. I do have the feeling that if you share a clause, that is like it won't happen often that you share a clause and afterwards you share a clause that's a superset of the clause you shared before, right?
I mean the other way around. So you discover later in the search that you have a clause that actually subsumes some other clauses in the set, and since you just perform it once, and then you can transmit this information to all instances of the of solvers, say this clause you don't care about, just delete it.
Yes, that might make sense. Yeah, I haven't really thought about that way before, but it might make sense. Yeah, we're generally interested in trying to somehow consolidate these in-processing and simplification routines to be effective on a more global scale and to cooperate better across the solver thread. So that might be one way. Yes.
Great. Thank you.
Okay, we have another question here.
Just an idea how to do some statistics about the overlapping pattern. So there are 2 extreme cases. One is if you have always the same overlap in all your experts, and the other one is uniformly randomly distributed. Have you done this, or is it maybe an idea to extend it like this?
So you mean you're looking at it from a global scale?
Yes.
And you try to, like, what would be a metric there? So Do you mean that on a visual level or in terms of a single metric you're computing? Not entirely sure what you mean or how to define that. Because like what we did, we looked at a global scale at a metric where one number falls out. That's this global overlap. And then we looked at pairwise, where we just look at two experts and we see how
pairwise.
Yeah, so those pairwise overlaps are what we got in those matrices, right? And that was only first two processes. Computing it for this was rather expensive, and also you don't see that much then. But we did look at those pairwise overlaps. Yeah.
Okay. Do we have any other questions? Dominic, I have one question. So you said there is a huge peak of shared unit clauses, and I wanted to ask you how costly it is to share them. Like, it would be quite counterintuitive if this was, too expensive.
Yes, like that is still one problem that our distributed solver, I want to say had, I hope it's had. In this year's competition, I made some changes. So the problem is that the clause export of malloc always prefers the short clauses. So it always prefers those units that are derived locally, right? So every solver process says, oh, I have many unit clauses, let me share all of them, and then it doesn't share anything else. And only during the aggregation do you actually notice that you have the same unit clauses all over again, like many times. So the clause sharing, until all of those unit clauses are flushed from all of the processes, clause sharing only boils down to sharing those units that everybody derived anyway, right? That's a problem. And what I did for this year's competition submission, we'll see how it fares, is that you can share infinitely many unit clauses, so they don't count towards the cost of your export buffer. And like that, you flush the unit clauses immediately, and at the same time, you can always already share other clauses. So I hope that this mitigates some of those problems, but originally and with the state of the solver, it is indirectly rather costly of having all of those unit clauses.
Okay, I see. And I have another question. So you said for if you run just one node, that means one thread, right?
One node is actually in that experiment 24 threads.
Okay.
Yeah, should have made that clearer. This is, or no, sorry, one node. It means 48 in this case, because we have this two-level parallelization. I'll talk about it next talk. But we have sockets on our machines, and for each socket, we launch a certain number of solver threads. So at one node, it's 48 threads in this case.
Okay, then I guess my question would be, maybe you don't have an answer because it's a weird one. How often does it happen that a clause is learned by, say, one solver, and then it is rederived by another one, or maybe the same solver because it was deleted somewhere in the process?
Yes. That's an interesting question. Like, how do the duplicates fare within one solver thread? So how often does it happen that a clause is reproduced by the same solver? I don't think that we looked into that. That would be interesting. So generally, within all of the threads, we have this distribution, right, where you see that many of the clauses are reproduced rather quickly, but it's in a different thread, right? So it's more like at this point of solving, many solvers produced that clause. But it would be interesting to see how often the same clause is produced by the same thread.
Yeah. Okay. Thank you very much. Okay, and talk number 3 in this session will be given by Robin, and it's going to be called To Link or Not to Link. That is a watch list.
Hello, hello.
To link or not to link, that should be the bottom.
Yes. Wonderful. Hello, everyone. I'm Robin. Before we start diving into the topic, I have to say I just landed this morning and sleep has been scarce. So please stop me if I start speaking French, okay? This presentation has for a goal not to explain something brand new, but actually, so I would like to prevent newcomers in the field to do the same mistakes I did last year. And purely selfishly, I would like to learn a bit more because I realized that I didn't know much. So there are the usual acknowledgements for money, but also I would like to point a special acknowledgement for reviewers that actually, like just reading the reviews, I learned a lot. Now, last year, almost for a day, I decided, okay, now I know enough about SAT solving, I will write my own. Spoiler alert, I was a bit overconfident. And so, for example, this is the thing I came up with, which is already kind of wrong, is I will represent the clauses using a fixed data structure containing a literal to a pointer to the literals, the size, and just the blocker. Quite simple, right? I know that's not how it's done in Minisat and other solvers. We will touch on that later. And then there is always a question, so watch lists, right? Watch lists is the thing that makes SAT solvers efficient. And how do you represent this? Well, typically you go for an array representation where you have pointers or references. For each literal that you want to propagate, you have a list of references to clauses that are watched by that literal. And so this would look like this. For example, L1 is watched by C0, C1, C2, C5, and you can see that the first, within the two first literals, L1 would be in there. Now, I was really optimistic and really enthusiastic, and I was wondering, can we do better? I mean, it's been like that for many, many years, so we don't know. So this is actually the better version that I kind of pushed under the rug because I wanted my life to be easy, is because basically in my version, we share the blockers among the two watch lists, right? So I have one blocker per clause. In the usual approach, we would have one blocker in the watch list, which prevents you from dereferencing the clause altogether. And also, the clause would be one big chunk containing also the literals. Now, this is relevant for the analysis later because I claim that the arguments I make with this data structures also hold with this one. But what if we could do better and simpler? It's actually not very simple. But basically, the idea is, okay, well, each clause is in two watch lists, exactly, modulo some intermediate states. So how about we just put it in two linked lists, right? It makes sense. So for example, the pointer is nice. For example, here the clause C0 is in the watch list of L1, so we just have one pointer to the first clause in the list, and we don't care about having them all. And then we see, well, L1 is the second literal that is watched, so we follow the reference, second reference to the second clause. Now, why do we want to do this? We want to do this because it's a little bit more compact. Intuitively, if you have a vector and you push stuff in there and then you pop it, right, it will increase in size and then usually will not shrink it back. So this space might be lost. With this instance, we just allocate memory when we create the clause, and then we don't need to do anything anymore, which is really nice. Furthermore, we remove one dereferencement level. So if you want to access a clause here, you first have to look at the watch list, and then you go to the clause. Here, you go right from the clause to the next clause, and you don't go through the watch list. That sounded smart in my head last year. So here is a summary. So basically, we can dereference less to access the clause, and we use less memory. Also, a nice feature is now if you want to insert something in the watch list, it's always O of 1, because you never need to rescale the vector, so you never need to reallocate it. Now the side, like the less nice things is that the bookkeeping is a little bit higher. And we will see how that impacts. Also, it's a little bit more tricky to handle. I mean, conceptually, this is maybe a little bit more complicated to put your hand around than this. Okay, so I wrote this code and I made some experiments, and every point below the red line is better with linked lists. Very promising indeed. So what is that? Well, let's see. Let's go through a watch list, okay? So let's say you are propagating not L1. So you will go to the watch list, go do the reference C1. You look at C1. You see the blocker is not satisfied, so you will have to do something. So either replace the blocker or replace the watch list. So you dereference the literals. Okay, nice. This clause is done. Second, okay, now we are lucky. The blocker is satisfied and we don't need to do anything. So we don't dereference the literals and so on. So this is what we dereference. Sounds nice. Now, what happens if you have a linked list? Same thing here. Blocker is not satisfied. You have to find a replacement. You follow the link to the next clause. Uh-oh. Where do you go? Do you take the up path or down path? Well, the thing is, you actually have to check. So you still have to dereference this pointer, which is not so nice. And then this process continues, and now we have dereferenced absolutely everything to go through the watch list. And so the blockers are very much less efficient than they used to be. And for reference, this is what we had before. And with the Minisat implementation, it's even better because we don't even touch the clause. Right. So is the dereferencement a problem? The answer is probably yes. So if you are like you take the array implementation and you artificially dereference the pointer, you see a significant increase in computation time just for this. But it does not explain everything, right? So like I don't know, 30%, maybe no, like 20% of the slowdown is because of this. The rest is basically bookkeeping. So for example, one thing that I would like to do is when you're propagating a literal, you want it to be the first or second in the clause. So you will just swap them. And there is a trick. You can do this in 4 assembly instructions without branching, which is super nice. So it just consists in swapping those 2 literals. But if you're doing this with a watch list, you can't do this. Because if you swap literals, you also have to swap the 2 references. So now you have a branch. And so everything becomes more complicated, and the bookkeeping is what I suspect is making everything much worse. Now, this idea is so good that I wasn't the first one to think of it. And independently, I mean, I didn't know about this. I wouldn't spend my time on this otherwise. This was actually the original implementation in SATO. And PicoSat does a great job of explaining like everything that I just explained, but better. Wrongly? Ah. Okay. Cesare claimed that in the original implementation. Okay. Well, see, I learned things. So it was a good thing that I came here. Now, one interesting thing is that in the PicoSat paper, the linked list actually performed seemingly better. And all online. Yeah, okay. It's working again? Okay. I think you scared the microphone. It behaves. So I would like to discuss with people in the room here as to why that is. Because maybe I made a mistake in my implementation and it could be more efficient. But this is a little bit puzzling for me. So what did we do? We re-implemented the linked lists without knowing that that was already tried, and it seemed to be much worse than the array implementation. And The arguments for dereferencing and for bookkeeping also hold in the Minisat version of the implementation. I am actually currently working in the machinery of my stat solver to test this for sure, but intuitively that seems to be the case. And basically the conclusion is it's not really a good idea, and please don't waste your time on this, unless I am proven wrong today, which I would happily be. Thank you.
Okay, thanks a lot, Robin. We have plenty of time for questions.
Yeah, so I think in PicoSat I didn't use the blockers, or if I used them, then only for binary clauses in a separate stack, but I don't remember. So you could do also in your scheme, you could just have a separate stack for the binary clauses.
Yeah, I checked that, and it does not seem to use blockers, but even, oops, wrong direction. Even without that, I mean, the blockers would mostly reduce this part, but the bookkeeping part is somehow more prohibitive, it seems, than the blockers alone.
By the way, I think you can also do the XOR trick for getting the right getting the right link, but I'm not sure about it. So anyhow, so I think like your bookkeeping argument, it's particular nowadays. It's more that if the code is simpler, the compiler works better. It's not like sort of it's not sort of that you're kind of have this extra work. It's the same amount of work, but the compiler cannot figure out some low level optimization, which
Right.
so compilers are very good at kind of code which looks like matrix multiplication, and the stack looks way more like matrix multiplication than
Yeah, that's a good point. And also when you're, for example, cleaning the clauses, like everything they satisfied, it's a little bit more tricky to do with the linked list scheme, because if you have an array, you just push everything and then you clean up the arrays later. Like say you leave all the deleted clause and then you do one pass through the watch list. But you can't do this here because you cannot have the clause in more than two watch lists, if that makes sense.
So
Oh, sorry.
in PicoSat, there was like one buffer containing all the clauses. And in your implementation, you have a separate chunk of memory per every clause.
Yeah.
And that could explain the difference, because I mean, if you have all the clauses in the same buffer, then probably you could have less cache misses. Like if you have clauses separately, so if you jump from one chunk to another, you are more likely to have a cache miss. And does it make sense?
Yeah, it makes sense. So the clauses themselves are together. It's just the literals are aside. So this only applies if the blocker is not satisfied. But that is true that if you have the linked list, you have to dereference. You have to dereference them anyway, and so having them more local might help. Yeah.
Yes, so one thing like in GIMSA tool, which is this multi-threaded solver we like I implemented 2 years ago for the for Flock 2222 competition. I actually have a mixed hybrid version of this, because in parallel solving, where you really want to keep the clauses shared, right? Not like what Dominic was doing, but you really physically share in memory the same clause. You have the problem that you cannot sort of use the trick of Minisat for with different threads to keep the two literals at the first positions, okay? And so that's why every thread actually has its own sort of watches, which are similar to the one in one of your pictures. And yeah, well, the other one. No, they have a third one.
This is
yeah,
1, 2, 3.
Yeah, okay. No, one where you sort of separate I think it's the other one. Yeah, this one where you sort of have the all the information about sort of watching local for every thread, and then the actual clause data shared. And but then it turns out that it's way faster to also, like, for every thread have some copies, some literals of the clause. So actually in GIMSA tool there are 3 levels, like, even. And that's the only part where I wrote documentation in the code. So I suggest you look at this and try to understand what I did there.
I will have a look. Thank you. I think there was a question in the back.
Yeah, it was basically going into the direction of what Alex said, like that the dereference is costly and that you jump more randomly through memory. And to my experience, it's like super fast to just iterate an array because then the next chunk of memory can be fetched before,
Exactly.
like before you actually want to read it. So it's all in the cache in
Exactly.
time. Wait only once.
I hope to get rid of this like completely and like just having for free, removing this up the array there, but it doesn't work.
Just another remark. There is kind of an open question whether it makes sense to put all the watches in a single arena, like Armin does, or to hold them in like just point to every chunk of watches separately for every literal. I mean, when you allocate watchers for a literal,
Yeah.
you can allocate it separately, like in a single chunk, the watches only, like right, and then or you could allocate a buffer, an arena, and hold all the watches there, but then you need to reallocate and and there is an overhead, so it's unclear what is better.
So having here pointers, so this would not be like in memory, but this would be separate, and then having pointers to those
So
blocks.
it is either for every literal there is a separate chunk of memory only for the watches, or there is one single close like watch buffer with all the watches for all the literals. These are the alternatives, and it's unclear for me which one is better. I don't know.
So the goal would be to share the blockers within the clause?
No. So you have a watch list per literal, right?
Yes.
So now one way to implement this would be to allocate watch list per literal for every literal in a separate chunk of memory.
Okay.
Right? And
okay.
another way to do it would be to allocate one single like watch buffer or arena where you have all the watches per every literal, but then you have more machination. You need to kind of reallocate and stuff like that. So while you're at it, it would be nice if you could experiment and tell us which option is better.
Yeah,
So
okay,
that was
might
my
as well.
remark.
I think that could be useful if literals that are like highly correlated somehow are close to each other.
I'm not sure, because then if you have this one arena, you need to reallocate because watches move.
Yeah.
So I'm
So, but it could make sense if like you dereference, I mean, you load in the cache one line that would overlap with the second one, for example. But this would not work if your literals are all over the place and then you go from 1 to 1000 to 3 to etc. I think.
there is I mean, it could be turned only experimentally. And
yeah, but that would be interesting. Yeah. All right.
Okay, a quick question, Robin. You showed us a very small table of results, and I just wonder how representative are the benchmarks? I think it was the previous one. Like
this one.
to get frustrated so much, is it really,
Okay, so I will be completely honest. Those benchmarks are not great because I use the 3 random SAT. The reason being that knapSAT as of now is not super performant and performs ridiculously bad on the SATComp benchmarks. And so this is what I use for debugging. But I think it's so slow, like it's a factor of 3. It's not a few percent, that it's relatively safe to guess that it should extrapolate.
Okay, I see. Well, thanks a lot for sharing your frustration with us, Robin. It led to very fruitful discussions.
Thank you.
Let's thank the speaker again. And for the coffee break.
So one question.
Oh, yeah?
Because we are looking at the link, I mean, taking the linked list into picture, performance drop is because arrays can be preferred for like better as compared to linked list. I mean, from the perspective, like the microarchitecture can help arrays.
Yeah, it could be. It could be. I mean, if you use the vector from C++, some very smart people have a lot of time on this to make it as efficient as possible. And the linked list is like a bit homemade. So probably vectors are more efficient also for that reason. If you spend as much time to design this, maybe you could make it a bit faster, but the question is it worth it, and is it going to be faster in the end? And I don't think so. That's fine, yes. Well, the closed locality is a good argument in the blockers too. Yeah. That seems like a good explanation. But to be fair, I don't know if it's really worth it, right? To make yeah, okay. Yeah, fair enough. What do you mean for incremental?
Yeah. So this
Okay.
data structure is backtrackable. While if you do these standard watches, it's much harder to backtrack, I think. Take this.
Yeah, we can take this offline. Thank you.